Okay, so welcome to the 7th episode of the Fractal Cosmos. You can call this the second of the blue episodes because of my blue chart here, and this is a very special episode because the equation of time and particle size is revealed here. Okay? I'm not going to do the derivation. The derivation is very simple calculus. It's based upon the measurement of how little r0, which is the radius of a fractal particle, changes with time. It's changing because it's continuously losing energy through the surface of the fractal cosmos, and over time it's becomes smaller and smaller, and yet the total energy must be split among the particles in the fractal cosmos, so we get more and more particles as well. However, right here we're just showing the relationship between the particles and the radius of the universe. So in the last episode I defined that the t0 as being the unit of time that it takes light to travel from the center of the universe to the surface. Well, guess what? Our universe is more than 13.7 billion years old in this fractal cosmos. In fact, it's gone through approximately 90 of these cycles in order to get to the very small atoms that we share, the very small substrate atoms. Of course, this diagram is not drawn to scale. These atoms are the size of protons or perhaps quarks. So to get to be that small, so that this ratio is 10 to the 26 meters divided by 10 to the minus 16 or 18, you get 10 to the 44. So to get that huge number you had to have a good 90 cycles or so. So our universe is quite old when measured in terms of the number of cycles, time cycles for light to travel from the center of the universe to the edge of the universe. Now if you measure the same period of time in terms of the number of vibrations of an atom, and you sum up those vibrations of the atom since the first moment that this substrate was formed, the odd thing is that you get the same number of vibrations that would be contained in 10 to the, that would be contained in 13.7 billion years. Just works out that way. Check the math in the treatise and you'll see a very interesting calculation there. However, the truth of the matter is these atoms have been around for a much longer time. If you look back just 13.7 billion years, you still have very small atoms. You still have your galaxies have been around that long. So there hasn't been a lot of evolution or galactic creation and so forth in the past 13.7 billion years. So when we're looking out with telescopes to the edge of the universe, we're not actually looking at the beginning of the universe. The light waves from the beginning of the universe are long since gone and dispersed after 90 cycles of this t0. So we got a whole different way of looking at time here. But then again, you know, you could also look at this in a warped sort of way as that early period of time was the early Big Bang, and it's a singularity which sort of draws a black curtain over those first 80 or 85 cycles, which in our method of reckoning is considered just a fraction of a second, but not this way. So this theory is worth looking into to understand cosmological phenomena, to shed some light on some of the astronomical observations. And that's all I'll say about that. For now, that certainly opens up a lot of questions We'll have to know more about these standing waves and the particle interactions before we explore those cosmological questions. And it's going to take a lot more people investigating them and aligning some of the ideas here with existing theories. But certainly opens up a new way of looking at the universe. Thank you.